Oops. Okay, so quantum physics. Now, what is it about? Quantum physics is the physics of small stuff, right? Like particles, subatomic particles. Okay, so basically it's the study of small things, right? So quantum physics, like there's this theory, right? It's just a theory, not sure it's correct or not, right? It's not been proven yet, and it's very hard to prove. That they say everything is made of like vibrating strings. Every single particle is made of vibrating strings. For example, if you take electron, right, is actually you zoom in into the electron, you zoom in and you see that it is actually not a particle. It is actually a string, like a small string vibrating at a specific frequency, and that frequency makes up the electron. Okay, which is kind of counterintuitive, because what we learned so far based on all the science textbook, right, we learn about particles, right, all this. So this remain as like a sci-fi theory, okay. So it's about the small particles, okay, the subatomic particles, small stuff, okay, that we call the quantum physics. Okay, now in here, starting from this year, you have this chapter in the SPM. Okay, so first we'll look at a few things in this chapter, what we study in this chapter. Now, first thing is quantum energy. What is quantum energy? Okay, there's this scientist, right? Very in early days, it says that light could exist as a quantized packet of energy that they call photons. Okay, now you see the word quantized packet of energy. What is it? Okay, I want you to think about like this. Let's say you have the sun. Okay, the sun give out all sorts of light, right? You give out electromagnetic waves. You have the infrared, UV, everything. And I want to think about light not as a wave. Okay, I know that you have learned wave. You have learned that electromagnetic waves, they behave as wave, right? They can refract, diffract, interfere. But you can kind of think of light as like a ball of energy. Yeah? Okay, it's like, for example, you have like a cannon shooting out cannonball. Here it is in my cannon, shooting out cannonball of energy. Okay, we call it packets of energy. The way you think about it like this. Okay, so our cannon is like the sun, shooting out cannonball, which is ball of energy, which has no mass, ball of energy. Okay, so it's like a lump of energy. When it hits something, then it's going to interact with the whatever that it hits. Okay, because it's energy, right? So it hits something, it's either being absorbed or it just went straight through. Okay, so it's no mass, it has no mass. No mass. So meaning that we can't really call it particle because it has no mass, right? Particle should be a matter, it has mass. But this one, just energy, no mass. That's why we don't call it particles, we call it photons. Photons. These are called photons. They are like particles, but they are not particles. Okay, they are basically energy, just energy. Okay, so you think about the light travel like a ball of many ball of energy in series, like traveling like this. Okay, that is we call photons. So this is the scientist, he proposed this understanding. He says that, okay, light not only is a wave, that it is also can behave like a particle that we call photon. Okay, so in wave, right, you learn about wave energy. The wave energy, how do you get the energy from the wave? The higher the frequency, the higher the energy, correct? Okay, the higher the frequency, the higher the energy. So you have like sound wave, and then you have X-ray on the other end, or the gamma ray. Moving from left to right, what happened to the energy? The energy increase, right? Energy increase. So X-ray and gamma ray has the higher energy than sound wave and the rest. Okay, so the energy of the wave, another way you think of it is like the energy is correspond to the amplitude. For example, like you have a wave, and then you have the amplitude of the wave. The bigger the amplitude, the bigger the energy, correct? The higher the energy of the wave. So if one wave has very high amplitude, then it has very high energy. So in the case of light, right, if we are talking about light, high energy means what? High energy means it's very bright. Okay, it's very bright and it has high intensity. That is for light. Okay, so in the wave understanding, from the wave understanding, we know that energy is amplitude. The higher the amplitude, the higher the energy. You can think of it like the tides, the water tides. The higher is the tide, the stronger it hits, right? So the higher is the amplitude of the tide, the stronger it hits, the higher the energy. This is from our wave understanding. But if you look at light as a particle rather than a wave, okay, particle like photons rather than a wave, then we have a different model of explaining it. We explain that the energy is actually coming from the frequency of the light and not from the amplitude. Okay, we have two models of understanding here. First is the wave model. Second one is the particle model. Later we'll come to this in more detail. Okay, so first is the wave particle, and first is the wave model. Second is the particle model. So the particle model, it explains light as a photon, and the energy of the light is actually get from the frequency of the photon that it is traveling. Okay, for the wave, it says that the energy is proportional to the amplitude. Two different models. Which one is correct? Which one is true? Okay, later we'll come to that. We'll save that for later. Okay. Right. So what is this? E equals to hf. This h is basically a scientist, very famous scientist. He came up with this idea, all this, right? So he's called Planck, Max Planck. So that's why he set this one after his name, the Planck constant. Okay, Planck constant, and you know the value here, h equals to 6.63 times 10 to the power of -34 joule second. Okay, so it's a constant, nothing, it doesn't change. And depending on the frequency, whatever the frequency of the wave, okay, of the light, you can calculate the energy. What energy is this? This is energy of one photon. One photon. It can emit millions and millions of photons, but here we are just calculating the energy of one photon. Okay, now, so before I go further, let's understand first about energy, quantum energy, okay? Energy level in an atom. So let's say I have electron here, okay? In an atom, the nucleus is positive charge, and we have electron around the nucleus, okay? What happened when one photon strike the electron? This is the electron, this is my proton. Now, remember the proton carry the energy, right? We can calculate it, E equals to hf. Okay, we can calculate the energy of this photon. When this photon go and strike this electron. Now, remember, one photon can only strike one electron. Okay, it cannot be one photon strike 2 or 3, cannot. One meet one. Okay, so one photon go and strike this one. What happened to the photon? It got absorbed, right? It got absorbed by this electron and it is destroyed. The photon is no longer there. So the electron absorbed this photon, and what happened to the electron? There are two scenarios that it could happen. First is that the electron might go to higher energy level. Okay, so the electron absorbed already and it got high energy, it jumped to higher energy level. Now it is here. Because the energy level of the electron is higher than original, so it cannot stay at the original place. It has to go, somewhere. So it will go to higher shell. Okay, So this process, what do we call this process? We call this process excitation. Excitation. Okay, so excitation means that the electron get energy and it got excited, right? Now, the second case that could happen is, okay, we have our nucleus, our electron, and same, we have a photon coming. The photon go and hit the electron, and if the photon has enough energy, if the energy of the photon is high enough, then it will have enough energy to pop the electron out from the atom. So meaning that this electron will, instead of going to higher energy level, it will straight away, it will jump out. Okay, it will jump out of the atom and it will go in the atmosphere. Okay, it will leave the atom, the metal, whatever, permanently. Okay, it will just leave the atom permanently. So two stages, two scenarios. One is excitation. This one is what we call it. This is we call ionization, right? Ionization. Or it could be emission. Okay, ionization or emission. Emission is the electron leaves the metal structure. Okay, leaves the metal structure. Ionization is the electron only leaves the atom, but remain in the structure. Okay, you have learned about this, right? All this ionization. So basically, when ionization happens, you have less, subtract one electron. Okay, you have one electron less, so it becomes a positive atom, right? It becomes an ion because the electron already pop out and then it stay in the lattice structure. So you have ion here. Okay. Now the other one is emission. Emission is like with enough energy, the electron will completely leave this metal structure, go into the surrounding atmosphere. Okay, so excitation, ionization, emission. Now, we look at excitation, right? What happened is that when this photon got absorbed by the electron go up higher energy level. Surprisingly, that electron, they don't like to be excited. They don't like to stay excited. They want to come back to their comfort zone. Okay. Once they leave their comfort zone, they want to come back. Okay, they will drop back. And then when they come back, right, they will release back the energy. Okay, now you see, the light comes in, okay, as photon comes in, absorbed by the electron. So the energy absorbed by the electron, it rises up, it excites, and then after a few seconds, after a period of time, the electron de-excites. Okay, de-excites. De-excitation. Meaning that it come down, okay? It come down back to the original orbit, and at the same time, it releases back the energy here. The energy absorbed by the electron is actually the same as the energy released here. Okay, it's the same energy release here. Okay, now let me draw this diagram bigger so that we can see clearly what is happening here. Okay, now I erase this first. Erase this. Okay, so let me zoom in, let you see this. This is our nucleus. This is the electron shell. So we have many layers of electron shell. Let's say I take here, zoom in. So you will see that here many layer, right? Many layer. So this layer is expressed as energy level. The base, we put n equals to 1, level 1, and we have level 2, level 3, and level 4. And anything higher than that, okay, we can say that it is ionized. Okay, so anything higher than this, at this stage, it's ionized. This shows the shell, and depending on where is the electron, if the electron is, let's say, at this region, then the electron already escaped the atom. Okay, because it has high energy already escaped, so the atom is ionized. Now, let's say the electron, initially it is here, okay, at the bottom. This one going up, right? Going up, the energy level actually increases. Okay, here, let's say it's 5 eV. EV stands for electron volt. Electron, okay, let me write it out. Electron volt. What is electron volt? How do you change it? 1 electron volt is equals to the charge of electron, 1.6 times 10 negative 19 joule. Okay, sometimes you will see this one. Sometimes we use joule, sometimes we use electron volt. Okay, both are energy, both are unit for energy. So you might want to take note of this lah. So when you see EV, you can convert to joule using this one. You times 1.6 times 10 power negative 19. Okay, so 5 electron volt. Okay, let's say this one is 7 electron volt and this is 8 electron volt. Okay, now let me show you what happens inside the atom. What is actually happening when the atom absorbs a photon? Okay, so here we have photon coming in. Okay, you can think of it like light or UV light, any light. Okay, photon. Now, got absorbed. Let's say the energy of the photon is 3 electron volt. Okay, so 3 electron volt. Now, initially the electron is here. Let's say this is zero energy. Okay, so if it wants to jump to higher shell, right? How many energy it needs? How much energy it needs? It needs 5 electron volt exactly. Okay, exactly 5. If it wants to jump to here, it needs 7. If the photon coming is only 3, what happened? Can it go halfway like this? Okay, I stay somewhere here halfway. Now, cannot. Huh? If the photon energy is 3, you see that 3 does not exist here, right? There's no 3 here. So what happened is that these photon will just pass by. It will not be absorbed. Okay, it will just pass by and then it will target another electron. It will target another electron that has 3 electron volt. So meaning that it has to absorb exactly the number in order to jump up to the higher shell. Okay, you can think of it like you are walking up a stair. If you take the step, let's say you want to walk up the stair, you want to go 3 steps up. Okay, you stretch your leg to 3 steps, right? If you stretch your leg to, let's say 2.5, what happened to you? You fall, right? Okay, you stretch 2.5, you cannot reach the 3 step, you fall, right? So there's nothing exists in between. It's either 3 steps or you fall. Okay, so same thing here. So you either 5 electron volt or you don't go. So meaning that not all photons, not all atom can absorb the photon. It only absorbs certain amount of energy, some specific energy level. Okay, this is very important. Huh? So write down here, atom only absorb specific energy levels, specific energy levels. Okay, so now let's say here we have 5 electron volt coming. 5 electron volt coming. Okay, can it go up? Yes, right? It can go up and it will absorb. So this one, it will absorb, it will go up to 5 electron volt. If you have 7 electron volt photon coming, then it will also jump to 7 electron volt. It will jump to here. So now the electron is excited. Excited. Here is not excited. Okay, so it stay here for some period of time, not long. And then after that, what happened to the electron? It will de-excite, right? It will come back down. Now, when it come back down, it can go in many different ways. It can go like this. It can go straight down, or it can come to here first, then continue go down. Okay, so if the electron goes straight down, meaning that it absorbs 7 electron volt to go up, by coming down, it releases how much? Also 7 electron volt, correct? Okay. So if it takes this second path, okay, this is the first path, this is the second path, meaning that the electron, it want to come down to 5 first, and then stay there for a while, and then come down again. Okay, we don't know, we don't know which path it will take. So let's say you take path number 2, then the electron will give out how much energy? 7 down to 5. So that's 2 electron volt. Okay, it will give out 2 electron volt, and then from 5 drop back to the original, it will give out 5 electron volt by releasing the energy. Okay, now what does it mean? It means that depending on what path the electron come down, it releases different amount of energy, right? This one it releases 7, this one it releases 2 and 5. So if it releases different amount of energy, that means it releases different frequency of wave into the atmosphere. You see, our formula E equals to hf. Based on whatever is the energy, we can calculate the frequency, correct? We can calculate the frequency, and if we can calculate the frequency, then we can calculate the wavelength, because V equals to F wavelength. Okay, I'll just put it in like this. hv over lambda. This is the speed of light, and we know the Planck constant. Knowing the energy release, you can calculate the wavelength being emitted. Wavelength emitted. Okay, so let's say I want to calculate the wavelength emitted when the electron come down from the 5 electron volt. Okay, it go from here, it come down to the original N1, N equals to 1, by releasing 5 electron volt. Okay, I take this formula, I take this energy, 5 electron volt. Okay, I put in my equations. So from this equation, I know that wavelength equals to hv over energy. Okay, this one you're already familiar with this equation, right? So wavelength equals to Planck times 10 minus 34 times the speed of light, because it's all electromagnetic waves, divided by the energy. Okay, how much energy is giving up? 5 electron volt, right? So 5 electron volt, I change it to joule. So I times 1.6 times 10 minus 19 over here. Okay, I change to joule. Calculate this, you will get around 250 Newton nanometer. Nanometer, that means this in this range is almost in the range of visible light. This wavelength is in the range of visible light. Visible light is about 400 to 700 nanometer. That is the wavelength of visible light. Okay, so meaning that based on this one, you know that by de-exciting, it produces light, right? It produces light. This atom produces light because it gives out this amount of energy, and this energy corresponds to the wavelength of visible light. Okay, and it has certain color. Okay, it has a certain color. So meaning that whatever energy absorbed by the photon, okay, whatever energy, whatever photon absorbed by the electron, they get excited and they can de-excite to give out another light. That is the point, the bottom line, okay? You can shine a light to the atom, okay? I can shine a light and then they absorb, and then they can also give out their own light. they can give out their own light. That we call it the light, the collection of light that they give out. We call it as the emission spectrum. The emission spectrum. Because it's not just one light. You see, this one that I calculated is just the 5 electron volt. How about the 2? You can also calculate this 2 electron volt. Then what is the wavelength? What is the light? What is the color of the light? Okay, because it can take more than one path to come down. Electron can only take one path to go up, but it can take more than one path to come down. That is why it can have more than one emission. More than one emission. Okay, so more than one emission, all these emission we combine together, we say that it has this emission spectrum. Later I will show you a few examples. Okay, a few images. Okay, so what do we know from here? We know that, okay, atoms only, let me write down here, atoms only absorb certain wavelength of light. Atom only absorb certain wavelength of light. Because of the energy level, you have to meet the exact energy, 5 electron volt or 7 electron volt. This is because of this reason that atoms only absorb certain wavelength. Okay, for any energy level in between, like the 3 electron volt, the 6 doesn't exist here. So if you convert to that wavelength using E equals to hf, you convert to that wavelength cannot be absorbed by the atom. Okay, so it only absorbs certain wavelength of light because of the specific energy level that it can jump to. And this is the first thing we have understood here. The second thing is that whenever atom absorb a wavelength, it can emit more than one wavelength. Understand? Whenever it absorb one wavelength of light, it can emit more than one wavelength. Why? Because when it de-excite, it can take many paths. So many energies being emitted, and that you convert to wavelength, you get many wavelengths of light. Okay? So now let me go to the next slide. See. Wait. Okay. Okay. Okay, now you see this one here. Let's say we have a light source. Okay, we have a light source and we shine the light through a gas. It can be anything, a gas, okay? A cloud of gas. And then we have a detector here. We look at the light that is passed through the gas, that has passed through the gas. Now, what is the color of the light from the sun? The color. All the colors, right? Because the light from the sun is white light. 白光, 白光是 all the colors. It consists all the colors. So when you shine the light across the gas, right? What do you see? You see that if you see from here, right? You see from here, you will see this one. What is this? This is a spectrum of color. And sometimes you see this dark strips. What is this? 这种黑线这种什么的? What is this? All these dark bands. It's like missing. The color is missing. What happened? These are the colors that got absorbed by the atom of the gas, the molecules of the gas. When the light passed through the molecules, it absorbs certain wavelength, and these wavelength happen to be these dark bands. Okay, so meaning that these missing color are the one that got absorbed. Remember, in the previous slide, we say about only specific wavelength it absorbed. Okay, so this spectrum, what do we call this spectrum? We call it the absorption spectrum. Absorption spectrum, because this spectrum shows what has been absorbed. This molecule absorbed this one, this one, this one, this one. Okay, and then apart from the absorption spectrum, right, we have another spectrum that we call the emission spectrum. The emission spectrum is when I see from here. Okay. If I change the position of my detector to up here, what do I see? Here, if the eye is here, right, I'm seeing what has been absorbed, right? If I'm looking from here, then I see what is being emitted. What is being emitted by the gas? Emitted by gas. Okay, so that is why we call this one the emission spectrum. Because this spectrum shows the color that is emitted by the atom when the electron de-excite. When the electron what? When the electron de-excites. Okay, so it's like you pass the sunlight to the gas, to the gas cloud, and then the atom absorb the photon. The electron get excited, and then they de-excite, they emit light. They emit light. Okay, they give out light. So what light is this? Ultraviolet light, blue light, green light, and red light. Okay, they give out these certain wavelengths. Okay, so maybe let's say this is the 5 electron volt, this is the 7 electron volt. Okay, you can calculate this based on the Planck's constant formula. Okay, so the energy and then the wavelength. So that is what I mean by absorption spectrum and emission spectrum. Okay, and also about the emission spectrum. Remember I said emission can be more than one, right? So the emission spectrum sometimes can have more color than the absorption spectrum. You can have, here you got 4 being absorbed. Sometimes the emission can have 8, can have 10, more than 4. Because when the electron de-excite, it can take many different paths. So many different possibilities of wavelength can be given out. Okay, yes. All right, now this is what happens in your fluorescent bulb. You have seen the fluorescent tube, okay, in your house. In your house, the long one. If you look at your ceiling, I don't know if you're still using the fluorescent tube, very long one, the old tube, okay, like this. Okay, let me draw it here. The fluorescent tube. What is inside? Okay, if I zoom in like this, inside you got 2 plates, one positive, one negative, and then inside the tube actually got gas. Is mercury gas inside. Mercury gas. What happened now when this negative plate actually it shoots electron? It shoots electron through the mercury gas. Okay, it shoots electron, and then the electron travels inside the tube across the mercury gas. So what happened is that these mercury atoms, right, the mercury atom will absorb this electron, and then they get excited, right? They absorb, they excite, and then they de-excite by giving out UV ray. Okay, it absorbs this one, de-excite, giving out UV ray. And then what happened is that these UV photons again got absorbed by a coating. There is a coating in the tube. okay, get absorbed by the coating in the tube, absorbed by a coating. And again, the coating excites and de-excite and produce light. Okay, this is how it works. Simple, okay, simple, just a simple process here. First, you shoot electron, right? So in the previous case, right, we talked about the electron excite by absorbing a proton, correct? Sorry, let me rephrase. We talk about the electron excite by absorbing a photon, right? It absorbed photon, and it got excited. But in here, there's no photon here. Initially, we are shooting electrons. So there are two ways that it can get excited. One is absorb photon. Another one is you bombard a electron. Bombard electron. Okay, you shoot an electron to this electron, then it can get excited also. Okay, there are two ways that you can excite it. So in this, we are using the second one. We shoot an electron to the mercury gas. So the mercury atom excited, de-excite by giving out UV ray, and then this UV ray and go on and hit the coating of the tube. Again, the coating get excited and de-excite and give out light. This is how the fluorescent tube works. Okay, it's based on, again, excitation and de-excitation. So in the end, you get white light, right? You get white light come from the tube. Yeah. Okay, so it's work based on the, again, the concept behind it. That the concept says that atom can absorb certain wavelength and then they can give out wavelength as well. They can emit wavelength. This is why we see color also. Okay, why you see the color of an object is red, because only red color is being reflected. All other colors is being absorbed. That is the reason. Again, atom absorb certain wavelength and certain wavelength that they emit. So you see red color of the object because the object emit red color. Okay, it absorbs all the color, but it emit red color. Okay, yeah. All right. Let me go to the next one. This one, right? All the gases, different gases, right? Different molecules, they show different absorption spectrum. Some gases, they absorb this color, some other gases absorb other different colors. Okay, it depends on the content. Depends on the content of the gas. What type of molecules is inside? For example, if you talk about hydrogen, oxygen, hydrogen absorbs certain wavelength, oxygen absorbs certain other different wavelength, not the same. So by analyzing the absorption spectrum, I can know, is it hydrogen or is it oxygen? Okay, because I know what type of wavelength hydrogen absorbs. So by analyzing the emission spectrum or the absorption spectrum, I can identify what is the gas made of. What is the gas made of? Okay, so I give you see some pictures here. This one, wait. Okay, now you see this one. Hydrogen, these are the emission spectrum, emission spectrum. So you can see specific colors that hydrogen give up. This one, this one, this one, this one, right? Silver, this one, you have more wavelength being emitted. Okay, so all these colors is being emitted by silver. So by analyzing how many colors being emitted, what are the colors being emitted, you can kind of know, you can find out what type of element is it. Okay, different element has different signature, different pattern. This pattern is for hydrogen, this pattern is for silver. So this is how the scientists, right, they they find what is the like what is the sun made of, what is the other planet made of, because it's very far, right? It's in outer space. You cannot actually go and collect the substance. You cannot collect the what do you say all the substance, right? To test it, you cannot. So you can only use emission spectrum to find out what is the component, the composition, okay, the composition of the gas. Okay, yes. Okay, let me go to the next slide. All right, now we come to here. The wave particle duality. What is it? Okay, just now we said that light can behave two different, based on different scenario, it can behave differently. One is based on the wave model and one is based on the particle model. Okay, let's understand this. You see the table here? Phenomenon, let's talk about light. Okay, now when I say light, it can mean all other light, the EM waves. It can be ultraviolet, it can be radio wave, it can be gamma, all the EM waves. Okay, so evidence that it is a wave, like diffraction, interference, and polarization. Let me give you one example. Like for example, you have a laser light, and then you let it pass through a slit opening. What do you see on the screen? You learned this in your senior one, right? What do you see on the screen? You see like a bright black. These bands, right? What is the cause of this? What's the reason that you see this? Interference, right? Interference. So the wave, they interfere, producing constructive, destructive. That's why you see this bright band, like dark band, bright band, dark band. Okay. Now this experiment prove what? Prove that light behave as a wave. Okay, because if it was not, if light was not a wave, you cannot see the bright dark fringe. So this experiment simply proved that light behave as a wave. So it is an evidence that light is actually a wave. Okay, so other evidences such as diffraction. So when the light pass through a slit, they can diffract like this. Okay, they diffract, they spread out in a wider area. This also proves that light is a wave. And also polarization, all this. Now, but the experiment of photoelectric effect, what is it? We'll come to it later, okay? In the next slide. This one actually prove that light can behave as particle. Okay, so we have a confusion here. Is it wave or is it particle? We don't know. Answer is both are also true. Both are true, okay? Just in different circumstances, it behaves differently. Now, apart from light, apart from EM waves, we have also particle. So electron is a particle. Okay, electron is a particle. Now, evidence that it is a wave, electron, surprisingly, electron can also diffract. Meaning that when you take a slit, okay, it's like a hole, a very small hole, and then you shoot electron. What happened to the electron? Because what we understand about electron is it is a particle, right? It is a particle, so it just goes straight through. But when they do the experiment, right, what they found is that the electron they shoot, the electron can also diffract one. How come? So is it a particle or is it a wave? Not sure, right? So again, both are true. Electron can also behave as a wave, and it can sometimes also behave as particle. So for example, the diffraction of electron and the interference shows that electron can behave as wave, and ionization shows that it behaves as particle. Okay, ionization is like, for example, the electrode. When you do the experiment, the chemical reaction, the electrode loses the mass, right? Become thinner and then less mass. It loses mass, it loses charge. So this ionization proves that electron is a particle because it loses mass. Particle has mass, right? But the diffraction, if you stick to the idea that electron is only particle, then the diffraction becomes very confusing. Okay, so that is why they come with this theory that they call the wave-particle duality. You see, light and electron can behave as wave or particle under different circumstances. This phenomenon is known as the wave-particle duality. It can be wave, it can be particle. It can be wave, it can be particle. Okay, so this is what it means by wave-particle duality. So the experiment you need to know, experiment like, for example, the question will ask you, what type of experiment shows that light is a particle? Then you know, okay, photoelectric effect. That experiment shows that it is a particle. What type of experiment proves that electron is a wave? You mentioned is the diffraction of electrons. Okay. The diffraction of electrons. Let's talk about this one. You see, diffraction of electrons. It happened that when you shoot an electron through a very small opening, this is not like normal hole. You have to make it so small that it's like the space between two atoms. Okay, you have two atoms, and the space between them is that small for the electron to diffract. Okay, that means, how do I achieve this? How do I achieve this? They use graphite. They use a very thin metal foil. Yes, they take a piece of metal, okay, but very thin metal foil, and then they shoot the electron through the metal foil. Usually it's graphite. This I'll show you one example how they do it. Okay, the metal foil is graphite. So they use the spacing between the atom very, very small, and then they shoot the electron across. What happened to the electron? They see from the screen. They see from the screen, it will appear like this. Okay, this is the front view of the screen. Like a dot, and then they see like concentric circle. Concentric circle means the circle having the same center. They see many circles having the same center like this. All these lines are green in color. Okay, because of the fluorescent effect. When the electrons strike the screen, it produces light due to the fluorescence. So you see many circles in green. You see, if electron is a particle, you wouldn't see this, right? You wouldn't see this. You only see what? You only see one dot. If electron was a particle, you only see one dot. But how come you see this? That means electron can behave as a wave. It can diffract. Okay, electrons can diffract. If it can diffract, means that it behaves as a wave. If it behaves as a wave, that means it has wavelength. Okay, that means it has wavelength. What is the wavelength of electron? Right, electron has a wavelength, yes. What is the wavelength of electron? Based on the scientist, he called this wavelength the de Broglie. Okay, de Broglie wavelength. It's in your book, right? What's the formula? You can calculate it. Wavelength equals to the Planck over the momentum. Okay, this wavelength is called the de Broglie wavelength, and it can be calculated using the Planck constant divided by the momentum of the particle. So you can write this as h over mv, mass into velocity. By knowing the mass of electron and the velocity that it is moving at, you can find out what is the wavelength of the electron. Okay, you can find out what is the wavelength of the electron. Now, it turned out that all particles has wavelength, not just electron. All particles, they have wavelength. But how come we don't see it? Because you see this formula, if the mass is very high, what happened to the wavelength? The wavelength is very small. That means heavy particle has very small wavelength. And because it has very small wavelength, so when they pass through a opening, the diffraction is very small. It's so small that you cannot see the diffraction. I repeat, remember diffraction in your wave chapter, when wave pass through the slit, they diffract, right? How do I increase the diffraction? How do I make it spread out more? Either I decrease the size of the opening, or I increase the wavelength so that it can spread out more. Okay, so the diffraction depends on what is your wavelength. If you want to have more diffraction, you want to have more wavelength, greater wavelength. So for heavy particle, because their mass is very high, right? So the wavelength of the particle very small that you cannot see, you cannot even see that it is diffracting. Okay, but you can only see with an electron. Why? Because electron, the mass is a few thousand times smaller than an atom. A few thousand times smaller than other particles, so the wavelength is larger and you can easily see the diffraction of electron. That is the reason why. Okay, so yes, all particle, this proves what? All particle can diffract. All particle has wavelength, not only the electromagnetic waves. Okay, so now give you a little bit of time to digest a bit. Okay, now just to show you some pictures. Okay, the formula, you have to take note of the formula. You have it in your textbook, right? Okay, so we mentioned about diffraction of electron, right? So you see, if you do the experiment, that you will see this, you see the picture on the left. On the left is the diffraction of light. Okay, red laser light. On the right is the diffraction of electron. Okay, behave like just like light. So it proves what? It's not only just a particle that's simple. Something's there. Okay, it can behave as a wave. Okay, now, because electron has a very small wavelength, okay, the wavelength is very small. What happened to small wavelength? If you compare to large wavelength and small wavelength, small wavelength, they can penetrate all the microstructure. What do I mean by that? For example, small wavelength, they can easily penetrate through small stuff. Large wavelength, right? Large wavelength, you can easily block it. For example, if you have like a, let me go to the previous slide first. No space here. For example, if you have, yeah. Okay. Let's say your wavelength is 1 meter. If you take a hole that is 0.5 meter, smaller than the wavelength, then you can completely block the wave, meaning that the wave cannot pass through already. Okay, cannot pass through. If you have a wave that is 1 nanometer, okay, very small wave, then it can pass through a hole of 1 nanometer. Okay, if this one, then it can pass through. So the smaller the wavelength, the more the ability of the wave to pass through, it can pass through. So because electron has a very small wavelength, so it can go inside the microstructure. Okay, it can go inside the microstructure, the atoms. That is why the electron microscope has a bigger magnification than the optical microscope. You see, if you compare the wavelength of electron and light, we have the wavelength of light, we have the wavelength of electron. The electron, you see here, the de Broglie wavelength of electron beam is approximately 1,000 times smaller than the light. Okay, so the wavelength of electron is 1,000 times smaller than light, so it can go inside this small structure of the atom and it can produce an image of this atom. So as a result, you get 100 times magnified image compared to the light microscope. Okay, short wavelength gives higher magnification. So the electron microscope is about 100 times more magnification than the optical microscope. So how do you compare the images? You can see here. If I see the image, this one. Now, this is the light microscope versus the electron one. On the left, you see the white and red blood cell, but on the right, you see more detailed picture of it. Okay, red blood cell and white blood cell here. Okay, all right. Okay, now before I go to the next one, I'm going to show you one video. Of the experiment of the diffraction of electron. How they diffract the electron. Okay, we'll pause a bit. We just watch some video. Okay, let me find the video. Okay, this one. Okay, you observe how they do the experiment, and you see how they diffract the electron using this electron beam. This electron tube.
This is an electron diffraction tube. It's a standard piece of equipment that we can use to show the wave behavior of electrons. Now, it's not used as widely as it might be, but let me show you how safe and straightforward it can be to use. This bit here is an evacuated bulb, and the biggest risk of using this equipment is probably that you might break this if you don't handle it with enough care. At this end, we've got an electron gun, a heated filament which releases electrons, which are attracted to the anode here, where they pass through a small hole and create a narrow beam, which travels across the tube and strikes the fluorescent screen here. Now in this tube, we've got a thin sheet of graphite here in the path of the electrons, and it's this which causes the electrons to be diffracted. And in order to use this, we need an extra high tension, or EHC, voltage supply. This is the power supply I use. It's got a high voltage supply here for the anode and a separate low voltage supply here for the cathode. We're essentially connecting two circuits. Now the reason why it's safe is that there's a high value resistor in series with the high voltage supply here, so the maximum current you can get out of it is not really big enough to do you any harm. Now before doing anything else, I make sure that all the switches are set to off and the voltage controls are set to 0. I then connect the 0 of the high voltage supply to the earth and the 0 of the low voltage supply to the same earth. Next, I connect the outputs of the low voltage supply to a couple of wires, so I'm ready to connect the cathode. And next I'll plug in the anode, for which I use these shrouded connectors, and that's so that there aren't any exposed bits of metal at high voltage. So that's the thing wired up and it's ready to turn on now. And I'm going to start by switching on the cathode, which takes a little while to warm up, but there you go, you can see it starting to glow now, which means you can turn on the high voltage supply. And I'm going to turn that up to about 3000 volts. Now, what I hope you can see is a green dot surrounded by fainter concentric green circles. And that's a diffraction pattern that's produced as the electrons fly through the graphite. Now, you can increase the energy of the electrons by increasing the voltage. You can see that's changed the diffraction pattern. The rings are closer together. And that's because at increased energies, the electrons have a shorter wavelength and they're diffracted less by the graphite. There's one more thing you might want to do with this apparatus, and that's to convince your students that the pattern is genuinely produced by electrons, that is, charged particles, and not by a beam of light. And to do that, you use a magnet. And if you bring that close to the beam, you can see that it deflects the image on the screen. And that certainly wouldn't be happening if it was being produced by a beam of light. Now, once you're done with the apparatus, obviously you turn it off, but it's best to wait a few minutes before disconnecting because it can take a while for the high voltage to die down to 0.
Okay, so you see the pattern of the diffractions, okay, of the electrons. It's like a dot in the middle, and then you see a few circles around it, right? That shows now this one, but it's very hard to see a bit, very hard to see, a bit fainter. So you see the concentric circle around it shows that the electron can be spread, okay, can be spread instead of just focus on one single. How do you know this one is electron? So he explained it, right? So using the magnet, if you put a magnet near it, you can see it move because electron has a charge. It get repelled by the magnet, okay, repelled or attracted by the magnet. If it was light, right, then the magnet cannot deflect the beam. Okay, I'm going to give you a short break. Now it's 8:08, so I'll give you like a 5-minute break. Okay, just to you want to go to the toilet, you can go. Okay, we'll come back at 5 minutes. After 5 minutes, okay. So we'll come back at 8:13. Okay, we come back. Okay, like Leticia. So just now we talked about the diffraction of electron. Now we go to photoelectric effect. So what is this experiment? This one is to show that light can behave as particle. Okay. Now basically, how it works. Okay, let me explain the concept behind it first. Here you have a metal with many free electrons. Okay, we have a light ray shining on the metal. Now, what we understand about light ray in wave theory is that just now I said the energy is proportional to amplitude, correct? The higher the amplitude, the higher the energy. And amplitude is the same meaning as brightness or intensity. The higher the brightness, the higher the energy. Okay? Now, meaning that if I turn on the light brighter and brighter and brighter, that means at certain brightness, it is able to give the energy to the electron and cause it to pop out, right? I want to emit the electrons. At certain brightness, I'm able to cause the electron to jump out of the metal. Because I can just increase the brightness until the energy is enough, right? But the problem is that is not the case. What they found is that if you keep on increasing the brightness, still there is no emission of electron. Still the electron cannot be emitted. So what is happening here? That means there is something that the wave theory cannot explain. Okay, so if we look at from the particle perspective, where energy is equals to the frequency, okay, then we can explain this. Because what they found is that if they shine light onto the metal, there is no electron coming out. But if they shine UV ray, then they see electron coming out. How come? Both ray, they put it at the same brightness. But how come the UV can cause the electron emission, but light ray cannot? Now, the difference is here. It's because of the frequency of the light. It turned out that they found there is a minimum frequency that we call it the threshold frequency, at which the electron must receive for it to escape from the metal. There is a minimum frequency that you have to meet. If you have a frequency of light that is below this threshold frequency, then no matter how you increase the brightness, no matter how long you shine it for a few hours, still the electron cannot come out. Okay, the electron cannot come out. So what is this threshold frequency? This threshold frequency just happened to be between the light and the UV spectrum, somewhere between here. If it was light, then the frequency is too low to have the electron escaping. If it was light, the electron is too low. Sorry, let me rephrase. If it was light, the energy is too low to cause the electron to jump. Okay, so only if it's UV, the frequency is enough to cause the electron to be emitted here. Okay, so now, since there is a threshold frequency, if we use the formula E equals to HF, this is minimum frequency, then we can calculate the minimum energy. Minimum frequency times by the Planck constant, you get the minimum energy that required to emit the electron. This minimum energy, we give it a name. We give it a name. We call this minimum energy the work function. Okay, the work function. Again, what is work function? Work function is the minimum energy to emit electron from the metal here. Okay, minimum energy to emit the electrons. So that means there are certain frequency of wave that cannot emit electron, which is light and all the ray below it, like radio wave, microwave, infrared, up to visible light. All this light, the frequency is too low, is below the threshold frequency, so the energy is below the work function. So no matter how you shine it, you shine light ray, you increase the brightness, you shine it very long period of time, still there's no electron coming out because there's not enough energy. So if you use UV, then you will see electrons start to come out because UV has a frequency bigger than the threshold frequency. This process of emitting the electrons by using light, by using UV light, whatever light, is we call photoemission. Okay, photoemission. What is photo? Photo means light. Photosynthesis, right? Light induced emission. The emission is caused by light. Because the electron is absorbing what? Absorbing photon. Absorbing what? Absorbing photon. One electron absorbs one photon. Okay? One electron cannot absorb two photons, only one photon. And remember, the energy must be exact. There are specific energy level that it absorbs. Okay? So again, this electron that comes out, what do we call it? They are called photoelectrons. Okay, photoelectrons. So electron emitted by using the light. Now, recall a bit what you learned in the electronic chapter. Remember the thermionic emission? Thermionic emission, where you hit a metal, right? You have a metal, you hit it, you use electricity to hit it, and then it will shoot electron, right? This is in the CRO, cathode ray oscilloscope. The electron got emitted by heating, by thermal. That is thermionic. This one, the electron is emitted by light. That is photoelectrons. So that one we call thermionic emission. This one we call photoemission, and the effect of it is called photoelectric effect. Okay, so what is photoelectric effect? It is the emission of the electron due to light, due to photon. Okay, so again, E equals to HF. This formula is very important. So if I put the threshold frequency F naught, then this becomes the work function. W equals to HF naught. Threshold. This is work function. So by knowing the threshold frequency, you can calculate what is the work function. What is the minimum energy you need to create photo emission? If your energy is below the work function, then there will be no photo emission. Okay, now, next slide. Here, you see. Photocell. Okay, this is the experiment to show that photo emission does happen. Okay, so we have a photocell. Photocell is like a light sensitive cell. Okay, so Inside, you have a light-sensitive metal. You shine a light source on it. It causes electron to come out. Okay, and then the electron, once they come out, right, they got attracted towards the anode, the positive charge. Inside is vacuum. Why must be vacuum? Because we don't want the electron to collide with any air particle. Okay, so what do you see here? What is the observation? The question was asked you, what is the observation? Okay, you see a deflection at the air meter. Okay, what does it say? So what? Deflection in the ammeter, because there's current flow, right? So that means this light source causes photoemission that complete the circuit and causes current to flow. So this is a simple experiment to show that photoelectric effect happens. Okay. Second one, the gold leaf electroscope. What is it? Okay. This is the second experiment to show the photoelectric effect. Basically, we have a zinc plate on top. Now, this zinc plate, we charge it negatively. We charge it negatively by rubbing it. Okay, we rub it, we charge it negative. So you have many negative charge here. And then this negative charge, they also travel down at this metal. And then they travel to the leaf also. This is a gold leaf, a very thin foil of metal. Okay, very thin foil of metal. Okay, so all of this, they are negatively charged. When I place the zinc plate on top of the metal, initially I charge the zinc plate and then I place it on top of this metal. Then all this become negative charge. And if the gold leaf and the metal has got negative charge, right, then they will repel one another. So you see the deflection like this. This is the metal. And then the gold leaf like deflected up like this, because negative, they repel negative. Okay, there's a force of repulsion. Now, what happens is that when you shine a UV light on top of the zinc plate, what happened to the UV light? The UV light will give energy to the electron and cause the electron to pop out, right? The electron escape into the atmosphere like this. Then what happened? When the electron come out, then you have less negative charge. When you have less negative charge, then the force of repulsion become weaker. And your observation is that the gold leaf will come down. It will move towards the metal plate. It will move towards the center here, the tube. Okay, so when you shine a UV light, you see this gold leaf come down. Okay, why? Because of the electron is discharging. The electron is discharging into the atmosphere. So the force of repulsion become weaker. You have less electron now. Okay, now sometimes they'll ask you, what happens if I switch this to a lamp, or I switch this to a sunlight? What happened? Is there any, what happened to the gold leaf? Answer is the gold leaf will stay deflected. There is nothing happened to the gold leaf. Can you guess why? Because lamp and sunlight, they are visible light, right? Their frequency is less than the threshold frequency. Meaning that they don't have enough energy to pop the electron off. Okay, they don't have enough energy. Their frequency is too small. So you need UV light. So as a result, if you shine a lamp or a sunlight, visible light, nothing happened to the gold leaf. It will stay deflected. Okay, so point number one, light travel as photons. This experiment proved that light travel as photon, and the energy is proportional to frequency and not amplitude. Okay, it proved that energy is proportional to frequency, not amplitude. Because if it was proportional to amplitude, then I can just increase the brightness, then the gold leaf will come down. I just increase the brightness, I just shine it longer, then the electron will come out. But it doesn't happen, right? So that means electron in energy depends on frequency and not brightness, not amplitude. Okay, number 2, one proton gives up its energy to one electron. Okay, so one proton can only go and hit one electron. If electron gains sufficient energy, so more than the work function, so what happened? He can escape the surface of the metal. And last one, high intensity or high brightness means more photon arriving per second. Okay, which will mean a greater number of photoelectrons emitted per second. Now, high brightness means what? Means in 1 second, there are more photon coming. Okay, so maybe at first, in 1 second, there's only 3 photon. And when you increase the brightness, that means in 1 second, now you got 10 photon coming. So this 10 photon will go and hit other 10 electron. So as a result, in 1 second, you get more electron coming up. Okay, so in 1 second, you got 10 photon, and in 1 second, you got 10 electron emitted. This is the intensity or brightness of this one. So high intensity does not mean high energy. Take note of this. High intensity does not equal to high energy. It simply means more photon per second. What does the energy depend? Depend on the frequency. This very important. This is based on what? This is based on the particle model. Okay, the particle model explanation. So the photoelectric effect proves that light is behave as a particle. Okay, behave as a particle. Okay, I want to show you one. Again, I want to show you one video on the gold leaf. Okay, let me find the video. Wait. Okay, using a gold leaf, this one.
One of the big ideas in physics is that light can behave as waves or particles, and this demonstration of the photoelectric effect is a really great way of introducing that idea. What I've got here is a zinc plate, and if you want the demonstration to work, it's absolutely essential to give it a good scrub on both sides with a bit of iron wool, and that just removes the surface oxide layer. I then place the plate on top of this gold leaf electroscope. I've also got an ordinary desk lamp and a UV lamp. Now, in order for the demonstration to work, this plate has to be negatively charged, and I can do that using the method of charging by induction. Now let me show you that again. I've got a Perspex rod here, which I can make positively charged by rubbing with this bit of cloth. I bring the rod close to the plate, touch the plate with my finger, remove my finger, then remove the rod. Now watch what happens when I shine visible light onto the plate. Absolutely nothing. That's actually a really important part of the demonstration. Your students need to notice that with visible light, nothing happens. But watch what happens when I shine ultraviolet light. You can see that the gold leaf immediately starts to fall. And that must mean that the UV light is somehow discharging the electroscope. We know that we started with negative charge on the plate, so the UV light must somehow be releasing the electrons. And the important thing to notice is that it's the frequency of the light that makes a difference. Remember, with a visible light, it doesn't matter how bright it is or how long it shines for, it doesn't release any electrons. Now, this phenomenon cannot be explained using a wave model of light, but we can understand it if we adopt the idea that radiation arrives at the plate as packets of energy, which we can call quanta or photons. A single photon of UV light can release a single electron from the plate. However, a single photon of visible light has less energy and so cannot release an electron. Now, this is a relatively simple demonstration to do, but it took the genius of Albert Einstein to explain what was going on. And it was for that work that he was awarded the 1921 Nobel Prize, not his work on relativity.
Okay, that's it. Right, so some of the formulas to know. We have the first one, E equals to HF. And then we have power. Power is energy over time, right? So the energy of one photon is HF over time. If I want for n number of protons, so I would times an n. Okay, if I want to find the total energy is I take what is the number of photon times into HF. Okay, so NHF, n is the number of photon. Okay, NHF over T, then I can take P equals to NHF. N is equals to N over T is the number of photon per second. Okay, in 1 second, how many photon is arriving? So like this. So you have an equation, power equals to NHF and E equals to HF. And also V equals to F lambda, V over lambda. So E equals to H V over lambda. Okay, 1, 2, 3. What else? You still got 1, right? The de Broglie wavelength equals to Planck over momentum. So H over mv. One, two, three, four. So far, you got 4 formulas that you are going to need in solving the questions. Okay, so for example, a 50-watt lamp emits red light with a wavelength of this. What is the number of photon emitted per second? This is N, right? So we have power equals to 50 watt. Wavelength is 7 times 10 minus 7. And we have N, we're going to find N. Which one do we use? We use the power one. Power equals to NH Frequency, I can write it as V over lambda. Okay, what is the V? The V is speed of light, speed of light. So N power wavelength over H speed of light. (50) times 7 times 10 minus 7 over H, Planck constant, times the speed of light. Okay, that is your answer.